Hi there. We talked today in class about numerical approximations. I call this our 4.6 section, but technically in your book it's both 4.6 and 4.2. The concepts that are located in 4.2 of our book I pull and I stick in with this lesson because I feel like they tie together well. All of these concepts, there are 4 of them total, deal with or look to address, I should say, this question: how can we approximate a definite integral? So you might ask, well, why are we wanting to approximate? We actually know how to calculate an integral, right? We learned that in 4.4a, this idea that if I wanted to take the integral from 0 to 2, for example, of x squared dx, well, then I would add 1 to the exponent and divide by that new exponent, and then do my f of b minus my f of a. Right? Like if I know how to calculate a definite integral, for sure, if I know how to get that correct answer, why would I want to approximate? And there are several reasons dealing with this. One example could possibly be like if you were given a graph, you were just told this graph is f of x. And you were asked something about the interval from 0 to 2, like is it an under approximation or an over approximation, and you have no idea what this graph is, right? We don't know whether it's some sort of square root or what it could be, because we only see a small segment of it and we aren't really given enough information to ascertain that, right? So in this case we would need to use an approximation. Okay. Another possible reason would be if you were given just a table of values and you were told all of these points are part of something that took place. It could be a function, or it could be something like water flow or something like that, right? At t equals 0, there was this much water. At t equals 3, there was this much water, etc. In such a case, you wouldn't have enough to be able to, again, determine the actual function, and so you might need to resort to an approximation in order to get kind of a gauge of about what the total area would be. Right, so that would be a couple of examples of why you'd want to approximate. Okay, when it comes to actually approximating, we have 4 different ways of approximating the area. Now I did really quickly here put in that definition for 4.3 again, just as a reminder that this is what we're looking at. We're looking at area when we're looking at a definite integral, that they're somewhat synonymous in a way, right? We're looking at area. Okay, so here are our 4 ways of approximating the area. The first one is called a left-hand Riemann sum, which I tend to shorten as LH for left hand. These are the rectangles made from the left of each subinterval. Okay, so I want to draw a quick little picture here so you can see kind of what we're talking about here. Okay, and so my picture is going to look like this. Okay, and that we are going to be looking from 0 to 2, and I'm going to go ahead and say that there are 4 subintervals. Usually you will be told, that should not be 0.25, I apologize, 1 second, it should be 0.5 if we have 4 subintervals. Usually you will be told how many subintervals there are in some way, shape, or form. We'll look at a couple of instructions that you could potentially see related to how many subintervals there are. In other cases, like 2 of your homework problems, they'll actually show you the picture. They'll give you the picture of the graph, kind of like we've done here, and they'll draw in the rectangles for you so you can see how many subintervals there are. Okay? And so when we're looking at approximating this integral from 0 to 2, we don't know what this function is. A left-hand Riemann sum draws in rectangles from the left of each subinterval. So for example, one subinterval is here from 0 to 0.5. And I can see here that it's not really going to be a rectangle technically. It's an approximation. But we can see where we could possibly draw in some rectangles. A left hand draws in from the left. 0 is on the left of this interval. And so I'm going to draw in from that point there, from where 0 occurs, right? What happens at 0. And my rectangle is going to be drawn through that point and across that subinterval. And there's my little rectangle here. I can figure out my base times my height and calculate its area. Okay? And so then we could do the same thing with this subinterval, 0.5 to 1. We draw in a left-hand Riemann sum. So you draw in a rectangle from the left. Same here with this third subinterval, 1 to 1.5, we draw in from the left. And 1.5 to 2, draw in from the left. And so what we're going to do a little bit later in these notes when we actually get into the procedural aspect of these is we're going to take all of our little rectangles that we've got and we're going to calculate each of their areas and add all of those areas together. Okay, in this particular case, we can tell that this is an under approximation. The reason we know that is because look at where your rectangle is compared to your overall area underneath the graph. This unshaded region here is area that we haven't accounted for in our approximation, right? It's an unshaded region that really should be part of the overall area. So I know that my approximation, my rectangles, are going to be too small. It's an under approximation. It's below the actual graph. Right? And sometimes that in and of itself is a question you might get posed. You might be given this graph, for example, and asked, would a left-hand Riemann sum be an under approximation or an over approximation? And so you'd look at this and you'd go, oh, well, that's an under approximation because if I drew in a rectangle from the left, it would definitely be below that graph. And so you would answer under approximation. Right? Okay, so a right-hand Riemann sum. This is the second strategy we've got. Okay, and we're going to use the same graph here, or roughly the same, obviously, because I'm sketching it by hand. It's not going to be perfectly the same, okay, but roughly the same. Okay, but a right-hand Riemann sum, okay, are rectangles made from the right of each subinterval. So when we do our 0 here, over to our 2. Now when we draw in our rectangles, we're going to start at the right, for right hand of each subinterval. So my 0 to 0.5 subinterval, 0.5 is on the right, and so I'm actually going to start at 0.5's point, right, instead of 0's point. And I'm going to draw my rectangle over that subinterval through that point. And so there's my rectangle. And I can already tell this is going to be an over approximation, right? Look at how far above my rectangle is over that graph, right? There's a lot of extra area in my rectangle that isn't actually part of the graph or isn't underneath the graph. Right? Right hand 0.5 to 1, 1 is on the right. 1 to 1.5, 1.5 is on the right. And 2 to 1.5, 2 is on the right. Okay. So that's what a right-hand Riemann sum, what we're calculating. Okay, and so we have our left hand, which is an under approximation. We have our right hand, which is an over approximation, which brings us to our third strategy. If one's an under approximation and one's an over approximation, neither are very accurate. Right, I guess it would depend on how small your rectangles are, but the way we've drawn them, it's not very accurate. There's a lot of extra space here, there's a lot of extra area here, right, over versus under. Okay, and so if we know that neither of those are very accurate, what if we tried to split the difference? Rather than doing the left or the right, what if we went right through the middle? Okay, which brings us to our third strategy here, which is the midpoint sum. These are rectangles made from the midpoints of each subinterval. So roughly the same graph here. Okay, but now rather than going from 0 or from 0.5, we're going to go from this midpoint here, right here at 0.25. And now our rectangle is going to go through that point. We go over to 0, over to 0.5, and we've got our rectangle. And this allows us to be hopefully a little bit more accurate, because you can see here towards the 0 side, my rectangle is an over approximation, but towards the 0.5 side, my rectangle is an under approximation, and they'll kind of help balance each other out a little bit. We'll get a little bit of a closer approximation. Okay, so not 0.5, not 1, but halfway in between, which is going to be what happens at 0.75. Right. Not 1, not 1.5, but 1.25. Not 1.5, not 2, but 1.75. And then you'd calculate each of their areas and add them together. Okay? Okay, so we have our left hand, we have our right hand, we have our midpoint. Midpoint got us closer, okay, which brings us to our fourth one. Our fourth strategy says we've got our left hand, which is sometimes an under, sometimes an over. In this particular graph, it happens to be an under. It might be an over approximation. We have our left hand, which is an under approximation. We have our right hand, which is an over approximation. It's a similar thought process to midpoint, kind of that idea of splitting the difference. And this thought process is, well, rather than drawing a straight line, a line parallel to the x-axis, what if we took this line here, which makes an under approximation, and we tipped it up? What if we sought to connect these 2 points directly? In doing so, you would have, hopefully, or not hopefully, you would definitely have a shape that's closer to this graph, right? This line would come right along the inside here of my function. And so it would give me a better approximation than either the left hand or the right hand. And when we do that, we get a trapezoid. It's turned on its side, but it is there, right? Which that is our fourth technique here, which is the trapezoidal rule. Trapezoids made between the left and right of each subinterval. So again, we're going to demonstrate this. It's going to be roughly the same graph again. Okay, but this time we're going to draw in a trapezoid, and we're going to connect both sides of our subinterval, the 0 point and the 0.5 point. And we've got here a trapezoid, and it's sometimes a little hard for people to see at first, so I am going to shade this one in fairly completely, just so we can see where the trapezoid is located, or how it's faced, I should say. Like I said, it is on its side. And so that trapezoid, again, it's a little hard to see, but that trapezoid's actually like this, right? You have your two bases and the height of your trapezoid. Because remember, the bases of a trapezoid are always parallel, the height is perpendicular to the bases. And you can see here when we drew in that trapezoid, there's a little bit of extra space right up here. So this is still going to be an under approximation, but it's going to get us a lot closer than either the left hand or the right hand. And so we do this again for all of these. And again, we'll calculate each of their areas and add them together. Okay, so those are our four strategies, and that brings us then to the actual procedural aspects of what we learned today. So far it's been more on the conceptual side as far as looking at a graph and seeing if it's an over approximation or an under approximation, and we are going to continue to reference that as we go through our problems here, but I do want to make sure we get into just kind of some procedural aspects. Okay, so that brings us to right hand, left hand, and midpoint sums. I'm leaving trapezoidal for a bit. We'll do that at the end of this video. I'm going to focus here on right hand, left hand, and midpoint, and we're going to do all three together. I will say this, your homework problems, none of them have all three together. I just think it's valuable to do all three of them with the same equation, just so you can see and compare what the different approximations generate. Okay, so our directions for all of these are going to be as follows. Find the approximations of the area using a right hand a left hand, and a midpoint sum. And then, like I said, they're going to tell you how many subintervals there are. These are two ways they could potentially tell you how many subintervals there are. They might say it very directly in words, right? Midpoint sum with 4 equal subintervals. Or they might write it like this: n equals 4. That n represents the number of subintervals, right? So the number of subintervals is 4. Or in other cases, like I said, for example, the 2 problems you have in your homework, they might just give you the picture with the rectangles or trapezoids drawn, and then you can see there are 4 subintervals because there are 4 shapes drawn in my picture, right? Or 5, or whatever the case might be in that particular problem. Okay? And our first example is going to deal with f of x equals x squared, and we're going to look at the interval from 0 to 2. Okay, to start with, to try to tie in some of that conceptual conversation we had here at the beginning of our notes, we are going to kind of do a quick little sketch. If you would like, you could plot this in your calculator as well to help you with your sketch. I'm just going to sketch it by hand really quickly because 0 to 2 is not that bad, and x squared is a pretty easy one to graph. So when I put in 0, I would have a point 0, 0. When I plug in 1, I'd have the point 1, 1. And when I plug in 2, I'd have the point 2, 4. And obviously I'm aware x squared is a full parabola, but I'm not going to draw the other side of the parabola because it's not in my interval, so I don't care about it. I only care about what's between 0 and 2. Okay, and we are going to do an approximation here, but before we get into the procedural, let's look at that conceptual. Okay, because if this was the picture you were given, you weren't told, for example, the function was x squared. You were just given this picture and you were asked, is the left-hand Riemann sum an under approximation or an over approximation? Well, with this particular graph, if we were wanting to test that, we could pick any point. I'm going to very quickly sketch that graph again, okay, so I don't mess up my notes. But you would pick any point on that interval, and you would say, okay, for example, that one, if I drew in a rectangle from the left, remember a left-hand Riemann sum, from the left, my rectangle would go that way. And I can see already that that rectangle is definitely an under approximation. And so you would answer them when they said, would a left-hand Riemann sum be or left-hand approximation, however they phrased it, would a left-hand approximation be an under approximation or an over approximation? You would say under approximation. They said a right-hand Riemann sum, under or over. You'd pick a point and you'd say, okay, if I drew in a right rectangle from the right, drew it in like that, that's definitely over my graph, so I would write over approximation. Okay. Okay, so let's go ahead and get into the procedural then. Procedural, left hand, right hand, midpoint. Okay. To do this, we're going to construct a table so that we can look at the values that we are working with. We need 4 subintervals. It's going to be an f of x table. And I know that I start at 0 and that I'm going to end at 2 over here. And I know that I've got to have 4 subintervals in between there. So the question is, where are those cuts being made? Okay, well, the easiest way to do that is to figure out what's the distance, what change has occurred between my 2 endpoints, what change has occurred over my interval, and divide that by the number of subintervals that they're asking you to do. Right, so in this case, from 0 to 2 is a difference of 2. And if I divide that by how many subintervals they want 4 subintervals, well, 2 divided by 4 is 0.5, or 1/2. You prefer fractions. Okay? And so that's how I'm going to cut up my interval. I'm going to start at 0 here, and then I'm going to count by 0.5 or halves, depending on what you prefer. I'm going to count by 0.5, and I'm going to work my way across my interval to 2. So after 0, 0.5 would be, well, 0.5. 0.5 from that would be 1. 0.5 from that would be 1.5, and 0.5 from that would be 2. Okay. And I know this looks like we've got 5 subintervals. We don't. We have 5 points. We're looking at intervals, distances between points. Our 4 subintervals are here. There's a subinterval, there's a subinterval, there's a subinterval, and there's a subinterval. And I'm going to draw that in our graph as well. Right? We have one interval from 0 to 0.5. We have another one from 0.5 to 1, another from 1 to 1.5, and one from 1.5 to 2. Here are our 4 subintervals. 1, 2, 3, 4. 4 equal subintervals. Okay, so here's how left hand, right hand, and midpoint work. If we set that up, we can draw in our left hand rectangles, right? And our left hand rectangles, starting with this first interval, 0 to 0.5, would start at the left, start at 0, and go across the interval. And so that would be my rectangle. Okay. I would have another one here starting at 0.5, going across, and another one here starting at 1, going across, and the final one here at 1.5, going across. So you're like, okay, fine and dandy, we already went over that. What does that mean in terms of my table? Okay, well, let's go ahead and finish filling in our table, and then I'll point that out. Okay, at 0, I need to know what is my f of x. Okay. For that, your table in your calculator comes in handy. If you go to your y equals, and you type in your x squared, and then go to the table, you can put in your x values and it'll auto-generate your y's for you. Okay. And so we get our y values here of 0, 0.25, 1, 2.25, and 4. Okay, just as a reminder for my 84s who are following along with me here, if you go into your table and it's not letting you plug in values, right, like this, I'm trying to plug in 2 and it's not letting me plug in, you need to go to your table set, which is here, hit second window, and change your independent to ask rather than independent auto. And when you do that and go back to your table, now you'll be able to plug in the 2. Right, now I don't have the right y equals in there, which is why it's not generating the correct answer. Let me go ahead and put the correct y equals in there so you can see the 4 you were expecting to see. Right, and now you'll be able to plug in all of your values. Okay. Okay, so here's where the rectangles come in then, and how they tie to the table. My rectangles here, for example, this first one that I drew from 0 to 0.5, its base, call this left hand, its base is 0.5. It's the distance from 0 to 0.5. Right? And in my table, that's located right here. It's the change in x. Right? My base of my rectangle, base times height, is that area. My base is 0.5. So the question is, what is that rectangle's height? Base times height, I'll have its area. If its base is 0.5, its height is whatever occurs at x equals 0, at this left-hand point. Well, that is 0. And so my height is 0. 0.5 times 0 is the area of that first rectangle. Okay, my second rectangle, its base, 0.5 to 1, is also 0.5. It's located here on my table. 0.5 to 1 is 0.5. And its height is what occurs at 0.5, at that left-hand point. Well, at 0.5, 0.25 occurs. So my base is 0.5, my height is 0.25. Okay, my third rectangle, 1 to 1.5, also has a base of 0.5, right, 1 to 1.5. And its height is what happens at 1, which is 1. And then the fourth rectangle, 1.5 to 2, is also 0.5, and its height is what occurs at 1.5, which is 2.25. Okay, so that's your setup. Base times height, base times height, base times height, base times height for your 4 rectangles. And if you add all those areas together, okay, you'll get your approximation, which in this case would give us an approximation of about 1.75. Now in actuality, this area is 8/3, or 2.666, or 2.667 if you round. Right, so we know that this is an approximation, but we knew that already. We knew it was an under approximation, I should say, because it was below the graph. So 1.75, not close to 2.666 really. It's definitely below 2.666, which we knew it was going to be. Okay, that's your left hand. Okay, in terms of a way to kind of process through these steps, okay, a left hand, you're always going to do these little triangles, these changes in x. That's going to make its way into every single one of our 4 approximations. You're going to continue to do these little triangles. Okay, but the left hand, you do that change in x, so the 0.5, times the left hand y. Right? Same thing here, second subinterval. Change in x times the left hand y. Change in x times the left hand y. Change in x times the left hand y. And that'll give you these 4 areas. Okay, right hand is going to be the same steps, but we're going to go from the right here, right? And so when I'm doing my base times my height, my base is still going to be 0.5 because the distance across this rectangle is still 0.5, but the height now is going to be the right hand y. Right? And so my right hand here, still going to have 0.5, still going to have the distance from 0 to 0.5, still going to have that base. But my height now is going to be what happens at 0.5, at the right hand side of that interval. And what happens at 0.5 is 0.25. Okay. And then we have our second 0.5, which is the distance from 0.5 to 1, and then the right hand, which will be 1. 0.5, the distance from 1 to 1.5, and then the right hand, which is 2.25. And then 0.5, distance from 1.5 to 2, and then the right hand. And when you calculate all those areas and add them together, you should get an approximation of about 3.75, which is an over approximation. That's definitely bigger than 2.666. We already knew it was going to be an over approximation. Look at our rectangles. They are above that graph. And so you know that your answer is going to be bigger than the actual. Okay? Same strategy then with the left hand, or as the left hand, just the other side. So you'll always have this with your right hand approximation. You do the change, right hand, change, right hand, change, right hand, change, right hand. Okay? So here's where midpoint comes in then, our midpoint approximation. Okay, the midpoint deals with what occurs halfway between our 2 endpoints. It gives you your rectangle there. Okay. And unfortunately, this actually isn't in my table, so I'm going to need to calculate some more values for myself. Okay, for these blue rectangles, they still have the same base, right? This blue rectangle still has a width of 0.5, 0 to 0.5. And so this 0.5 that I calculated, these triangles, are still going to be part of my approximation. Like I said, they're going to be in every single one of your approximations. Okay, so we have 0.5 times, but now we aren't going to use 0 or 0.25. We're going to use whatever happens here in the middle. And you want to be careful, don't calculate the middle between 0 and 0.25. We want to know actually what happens in that middle. The middle is here, right? Halfway between 0 and 0.5 is 0.25. I want to know what is the y value for 0.25, right? What's actually in the middle of this interval? What actually happens at 0.25? Okay? You want to be careful you aren't calculating halfway between these two values. We want to find out what happens at halfway between our x values. Right, and so I'm going to go to my calculator again, where I have my x squared still plugged in, my function still plugged in, and I'm going to plug in 0.25. Whoops, sorry. In my table, I'm going to plug in 0.25, and I'm going to get 0.0625. That's the height of my midpoint rectangle. Right, it's right here, 0.0625. Right? Okay, halfway between 0.5 and 1 is 0.75. I want to know what happens at 0.75, so I'll go ahead and generate that. That is 0.5625, and that's going to be my second rectangle. Still a difference, still a base of 0.5, but now my height is 0.5625. Third rectangle, what happens at 1.25? Okay, well, for that one we get 1.5625. Okay, and I'm going to go ahead and pull the rest of this sum down here. Okay. For my last one, which is halfway between 1.5 and 2, which is 1.75, and you get 3.0625. And when you add all those together, or I should say calculate all the areas and then add them together, you get 2.625, which is a much closer approximation to our 2.666 than the other two, right? Midpoint gets us a little bit closer usually. Okay, and so those are your three approximations, or the first three approximations, I should say. Okay, when you're looking at our notes online, we walked through two additional problems, or I should say I technically gave them to your classmates to attempt on your own. It's the exact same steps as what we've done here. So I'm going to go ahead and walk through another one a little bit faster than what I've just done here, although I'm still kind of explaining all the steps. Okay, so our second example is going to be the same instructions. Find the approximations of the area using a right hand, a left hand, and a midpoint sum with 4 equal subintervals n equals 4. Okay, but our function this time is going to be the square root of x squared plus 3. 0 to 8. Okay, so what I did for your classmates when we got to this one, this was kind of a guided problem, not entirely on their own. And so I'm going to do that kind of similarly here on the video. My recommendation would be to pause when I give an instruction and take the instruction. I'm not going to wait as long as I would as though we were in class, you know, because in class I'm basing it off of what I'm seeing on people's papers, and I'm basing off conversations I'm hearing and that sort of thing. So pause the video and do what I've instructed you to do, and then turn it back on when you've attempted it or gotten stuck or whatever the case may be, or have an answer if you get that far. And then listen to the next set of instructions, and we're going to walk through this one kind of together here. Okay, so the first step. It's your choice whether or not you want to graph it. I typically like to graph it myself, and so I'm going to go ahead and just kind of give a quick little sketch here so we can take a look at it. 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. So roughly, it's not a perfect sketch, it's a rough sketch. And again, you can put it in your graphing calculator. The reason I like to sketch it beforehand is I like to already have an idea of sort of how my numbers should compare. I like to look at it and say, okay, if I had a left-hand Riemann sum and drew that in, then I know it would be an under approximation. And if I drew in my right-hand Riemann sum, then I know it would be an over approximation. And so I already know that as I'm going through the process of calculating my left and my left hand should be smaller than my right hand, right? The left hand's going to be an under approximation, right hand's going to be an over. So you're going to want to make sure you see that in your numbers. Right? Okay, so my first set of instructions for you is this. We know that we have 4 subintervals. Okay, so take a moment and think to yourself, if we have 4 subintervals over 0 to 8, where am I cutting those intervals? What are going to be my distances? What are going to be my widths of each of those subintervals? Okay, and so we mentioned this before, but one more time, subintervals equal subintervals. The easiest way to do that is to say, okay, what's the distance from 0 to 8? 8, or difference between 0 and 8, that's 8. Divide by how many subintervals you need. 8 divided by 4 is 2. And so I'm going to be counting by 2s. I'm going to be cutting at 2s. Okay? And so we're going to go ahead and build our table here. Counting by 2. So starting at 0, we're going to go 2, 4, 6, 8. Okay. Those are our 4 subintervals. Okay, my next set of instructions, and you're going to want to pause the video because this might take you a little bit. I want you to generate those y values, and you can either do that by hand by plugging in, or you can use your table and your graphing calculator. But what are the y values for those points? Okay. Okay, so we've got our square root x squared plus 3 that I've put into my y equals. And then when I go to my table and I type in 0, 2, 4, 6, and 8, okay, I get my values here, which are root 3, root 7, root 19, I apologize, root 39, and root 67. Okay, now if you are going to use decimals, you want to be really careful to not round or truncate early. If you're going to use decimals instead of roots like I've done here, then you're going to want to make sure that you've stored the decimal in some way, shape, or form, or used the entirety of the decimal. You don't want to round early because that's going to skew your final answer, right? So you either need to make sure you've written it as a fraction or as a radical, or that you use more than just 3 decimal places as you continue from here. Make sure you don't round early. Wait till the very end to either round or truncate to 3 decimal places. Okay? Okay, my next set of instructions for you. All of our approximations deal with the same widths, right? Same widths all across the top here. Okay, and so take a moment. What are those widths? Okay, and hopefully you're able to figure out that every single one of those, in this particular case, is 2. It does not have to be true, by the way, that they are all the same. In this case, we were told 4 equal subintervals. It is possible that you might be just given a table and that those change in x's might be different. It might say 1 and then 3 and then 2 and then 1 again, right? If you were just given a table and you didn't have to generate it. Okay. In this case, though, they all happen to be the same. Okay. Which brings us to our next step here. I want to know, what is my left-hand Riemann sum? Okay, and so just our setup, take a moment and see if you can set that up. See if you can do your base times your left-hand height. Base times your left-hand height for our 4 subintervals. Okay, so here we go. Our base of our first subinterval here, our first subinterval is 0 to 2. Our base is 2. And our height is the left-hand height, because we're doing the left-hand Riemann sum. And so we're going to use root 3 as our height. Second subinterval, distance of 2. left-hand height. Third subinterval, distance of 2, left-hand height. And fourth one, distance of 2, left-hand height. Okay, so there's your left hand. And then when you multiply all those, add them together, you should get an approximation of about 29.963. Okay, so my next set of instructions for you is we want our right hand approximation. Okay, and so see if you take a moment to set that up. Base times right hand height. Okay, so our first subinterval is here, 0 to 2. We have our base times our right hand height, which is that root 7. Second interval here, 2 times right hand height, which is our root 19. Third subinterval, 2 times right hand height, which is the root 39. And fourth subinterval, 2 times the right hand height, which is root 67. Okay, when you calculate all of those, you should get 42.870. Okay, next up we have our midpoint. Okay, so my first set of instructions related to midpoint is we need to actually figure out what happens at our midpoints, what are our midpoints. And so between 0 and 2 here, between 2 and 4, between 4 and 6, between 6 and 8, what are the midpoint x values that we're going to be calculating? Okay, and you should have gotten 1, 3, 5, and 7. Okay, and so the next set of instructions, if those are the x values, what are their heights? What happens at 1 when I plug in 1? What happens at 3 when I plug in 3, at 5, and at 7? Take a moment and figure that out. Okay, and so when you plug in 1, you should get 2. When you plug in 3, you should get 3.4641, which is the square root of 12. When you plug in 5, you get 5.2915, or the square root of 28. And 7, you should get the square root of 52. Okay, and so my final set of instructions here related to this problem are with those values. Now see if you can set up your midpoint approximation. Okay, so midpoint, we still have that same base of 2, but my height now is what happens at the midpoint. In this first rectangle, that's 2. In the second rectangle, that height is root 12. In the third rectangle, that height is root 28. And in that fourth rectangle, that height is root 52. And when you plug that in, you should get 35.933. Okay, so when you look at your notes online, there is a third example problem here. This is one that I gave to your classmates to try completely on your own. If you would like to try it, I might recommend it. All of the answers are on the notes online, so you can check your answers. And it would be a way to just kind of validate that you are in fact understanding this. At the end of these 3, I asked if, having done one on their own, if your classmates felt good to move on, and they felt like they were good to move into our trapezoidal approximations, which is the last one. So that's where we're going to head next. Okay, so this is our last section of these notes, trapezoidal approximations. Okay, trapezoidal approximations in many ways are going to seem very similar to the left hand and right hand Riemann sums. Okay, the first thing that we do need to review though is what is that formula? What is the area of a trapezoid? Okay, and the area of a trapezoid is 1/2 sum of the bases times the height. Okay, our instructions on this one. Okay, are going to be to use a trapezoidal sum to approximate the integral from 1 to 2 of 1 over x squared with n equal to 4. Okay. So again, I tend to like to sketch the graph just so I can kind of see what I'm working with. So I'm going to go ahead and do that pretty quickly here. The graph is of 1 over x squared. I only care about what happens between 1 and 2. And again, you can put this in your calculator if that's easier for you. But just so I can kind of get a quick little glimpse. It's a rough sketch, not perfect, just a rough sketch of what we're working with here. Okay, and in this one, we're told n equals 4, which means our subintervals in our table are going to be intervals of 4. Or I should say they're going to be 4 subintervals, not intervals of 4, but 4 subintervals. We're going to cut it up, right? And so that's going to be our first step. It's the same first step as the left hand and right hand Riemann sums and midpoint sums. Okay, we need to construct that table. I'm going to be starting at 1, because that's that bottom bound there. And I'm going to be counting to 2 with 4 subintervals. So the question is, where am I cutting? Okay. And so one more time. To figure out where to cut, figure out what the distance is. Distance from 1 to 2 is 1. And divide by how many there are. How many subintervals there are. 1 divided by 4 is 0.25 or 1/4, if you prefer it that way. Either way. Okay, and so we're going to be counting by 0.25s. 1 plus 0.25 is 1.25, or 5/4, 1.5, or 3/2, 1.75, or 7/4, and 2. Okay. And we still need to generate our f of x values the same way, so you can put this 1 over x squared into your y equals and generate your table. You should get 1 16/25, 4 ninths, 16 49ths, and 1/4. Okay, and so here's where our trapezoidal starts to differ just a little bit. Okay, our trapezoidal sum is using this formula, 1/2 sum of the bases times the height. Well, it's potentially a little tricky at first to see what constitutes my bases and what constitutes my height. Okay, and so I'm going to go ahead and cut this up really quickly here so we can see our subintervals. That's my 1.25, 1.5, and 1.75. And here is going to be my first trapezoid from one endpoint to the other. Right? There's my first trapezoid. Sorry, it's a little bit wiggly, but you get the picture, right? And you can see here, what's my base? My base 1 and base 2, I should say, are actually the y values, right? Because remember, this trapezoid is on its side, technically. Right, so my base, okay, bases are my y values. My height of my trapezoid is this little portion right here. It's the distance from 1 to 1.25. And the distance from 1 to 1.25 is 0.25. It's that change in x. Like I said at the beginning, this change in x is going to be there for every approximation. It changes its name between approximations. Sometimes it might be called width, sometimes height, sometimes base, okay, but it's going to be there in some way, shape, or form. Okay. With the left hand, we did that change left, right? With the right hand, we did that change right. With the trapezoid, we're going to do the change. It's going to be my height right there. Do the change and then both. Both of those values are my bases. One's my base 1, one's my base 2. So left hand use the left, right hand use the right. Trapezoidal use both. Okay. And so that's what brings us to our work here. Our trapezoidal, we're going to have our 1/2 sum of the bases times the height. With my first subinterval here, okay, we have our base 1, which is 1, plus my base 2, which is 16/25. And my height is this 0.25. With my second subinterval, we have base 1, which is 16/25, base 2, which is 4/9, and my height, which is 0.25. And you're going to keep this up for the other two subintervals, 1/2, 4/9 and 16/49. For that third subinterval. And bringing that sum down here then for the last subinterval, we have the 16/49 and the 1/4. Okay. And then when you plug all of that in, you get approximately 0.508. And in actuality, the technical approximation is 0.5. And so you can see compared to 0.5, 0.508 is pretty close. Right? So trapezoidal is a fairly accurate approximation. Okay? The last part of the notes, when you look at it, or I should say the last example in the notes, was one that I gave to your classmates to work through on their own, and so I would do the same strategy or same recommendation to you as I did with the prior little section, is take that last example that you see in those notes, try it on your own, compare it to the answer you got there, and when we pick this up again on Thursday or Friday, depending on when you have me, we'll take another look at it and see if we can wrap up any loose ends you might still have after this video. Okay, good luck.